A topological sort is an ordering of the vertices in a directed graph such that for every edge between two vertices u and v, u comes before v in the ordering. So for instance, the vertices may represent individual tasks that need to be performed, and the edges represent constraints requiring, for instance, that one task come before the next. And so this is why we use a directed graph. We can only do topological sorts on directed graphs. And the edges signify the constraints that exist. And so in such an application, for instance, for scheduling jobs and tasks, the topological ordering then is just a valid sequence for the tasks. And there may be multiple valid sequences, as I'll point out in the example that we give. For instance, if two tasks are unrelated, there's not an edge between them, and they can both be performed at a particular point in time, it's fine to take either task and execute it. So a topological ordering is possible if and only if there are no cycles in the graph, there are no directed cycles in the graph. So it must be performed on a directed acyclic graph, also known as a DAG. So the topological sorting algorithm is fairly straightforward. We can use a stack, and I'll show you an example using a stack. When we use a stack, we focus on vertices that have out degree 0. And if you'll recall from 3080 and from when we spoke earlier about the degree of a specific vertex, the number of edges that are incident to that vertex. The out degree, obviously, in a directed graph means the edges that are outflowing from that vertex. And we can use a queue, and we really don't use a queue. We just use direct output when we focus on vertices within degree of 0. So the pseudocode is shown below. We pass the topological sort function a digraph, and it goes through every vertex, and it finds a candidate vertex. And when it does, it basically either outputs that vertex directly, or it pushes it onto a stack, and it removes that vertex and all edges that are incident with that vertex. And then basically we update as we go through. We expose other vertices that can be pulled off for the next iteration. And the example will hopefully make that clear. And we will do this until the digraph is empty. Once it's empty and we've output the information, that's the end of the topological sort. So let's look at just a small example. So we have the small graph. We're beginning, this is our starting graph here. And okay, so this is our starting graph. And we're focusing on direct output. We could put these into a queue, but then we immediately remove them. So we're going to focus on removing vertices that have in degree 0. This is known as source removal. Okay, and so as we look at this directed graph, which we're given, there are only two vertices within degree 0, and either one of them could be taken. Okay, and that's C1. There's nothing going into C1, and C2. There's nothing going into C2. Every other vertex, C3, has incoming edges, C4 has incoming edges, and C5 has incoming edges. So we're just going to keep things simple by removing these in order. And so in essence, what we do then is we delete C1 and we output it. Okay, this is the direct output method. We delete C1 and we delete all edges incident to C1. Okay, so that looks like this, giving us this graph in the center, in the middle. Okay, and we've output C1. Now we only have one other choice. There's only one remaining node that has in degree 0, right? And I'm going to point to the correct, and that's this one. Okay, so we don't have the option of removing C3 because it has an in degree greater than 0, C4 or C5. And so we remove this particular vertex and all the edges incident to that vertex, and we output it. And so what we're saying is, let's first do task C1, and then we'll do task C2, like we've shown here. We could have just as easily said, let's do task C2 and then task C1. It turns out that both of those tasks form dependencies for task C3. Okay, so there are constraints on C3. Once the graph looks like this, which it does now, the only other edge we can pull, the only other vertex we can pull is C3, and so we pull C3 and we remove all edges incident to C3 and we output C3. Okay, and finally we're at this stage now, and the only node that can come off is C4, and so we remove C4 and we output it, and then finally we're just down to C5. It's got in degree 0 and we remove that. It has no out degree. We output it, and this is a topological sort. Now this is a fairly easy example. You may see something like this on the exam. It will not be a simple graph like this. It'll be one that has a few more dependencies, but all you have to do is follow the process. Really, as long as you ensure that you're not violating the in degree 0 when you're doing source removal, regardless of the order that you pull them off, as long as both those nodes can be pulled off, it would be a correct answer in that case. Okay, let's look at one with sink removal. The only thing that's different about sink removal is that we will create a stack, and it's not a very good stack, but we will basically, and we'll focus on out degree 0. Okay, and this is called sink removal. Okay, so what has out degree 0? Well, this has out degree 1, has out degree, this has out degree 2, this has out degree 1. This is the only one that doesn't have out degree 0. That has no out degree, so we will remove this and we will push it onto the stack, and we will remove all edges incident, giving us then C1, C2, and then C3 here. And make this a better one, and C4. Okay, we're looking again at out degree of 0. Let's label our edges just to make sure. And the only one having out degree 0 here, that has out degree 1, this has out degree 1, this has out degree 1. C4 is our only candidate. So we remove C4 and we push it onto the stack, and the graph now looks like this. Okay, and so I'll redraw it, C2 and C3. And there's an edge here and an edge here. This is the only one without degree 0, so remove it. And remove all edges incident to it and place it on the stack. Okay, now I have 2 edges without degree 0. This is where I am now. Okay, these edges, 2 vertices, I'm sorry, I have 2 vertices without degree 0, and I could take either of them. Okay, since this is a stack and stacks reverse things, we're going to take the higher one. So we take away this one, we place it on the stack, and finally we're left with just C1, and we take this away, put it on the stack, and then pop until stack empty. Okay, and output. Okay, so that's just going to reverse the stack, and it will output C1, right, C2, C3, C4, and C5, right? So this is what we'll end up with as our final order, final output order. Okay, and that's topological sort. Again, the key to this problem when you see it on an exam is just to follow it deliberately and carefully, and ensure that you're not violating the out degree or the in degree based on which one you're given. And that's topological sorting.